for 16,000. Which of these square numbers also happens to be the sum of two smaller square numbers? 16, 25, 36, 49.
This is hard to do math when you're sitting up here. I'm going to go with the audience on this, and I'm going to say A, final answer.
Oh, Ryan, the audience is not right. I'm sorry. It was B. It was 4 squared plus 3 squared is 16 plus 9 equals 20.
I love that clip because it not only shows you how knowing perfect squares might be useful in a math class, but it could eventually, or knowing them could eventually win you $16,000 someday. So hopefully we know that perfect square number line that we used about, or we talked about in the last video, because we're going to be using it again today. We're going to be talking about adding, subtracting, multiplying, and dividing square roots today, and we're just going to start off really easy with adding and subtracting. These aren't too bad. It's almost like combining like terms like you're already used to doing with x's and y's and all that fun stuff. But what's important about adding and subtracting radicals or square roots is that you have the exact same number or term underneath the square root or radical symbol. So like I said, it's just like combining like terms. We're used to doing 2x and maybe a plus 3x. We know to combine those like terms, since x is exactly the same as x, we can add the coefficients out front, which would give us 5x. But on the other hand, 4x maybe plus 2y, we really wouldn't be able to do that because x and y are not like terms. They are not the same exact variable or the same thing. So we can simplify or combine like terms, whereas if they are different terms, they have to stay the way they are. Okay, we can't combine them. So what I like to think about, my little thought process when we are adding or subtracting radicals that are exactly the same underneath, like this 7 and 7, we add the outsides but keep the insides. So if we just take a look at number 1, we can kind of think about this as 3x plus 2x, because notice how this radical 7 is exactly the same as this, just like an x is exactly the same as x. So we can add the outsides. 3 and 2 give us 5. And we can keep the insides since they are the exact same value. So when we add these two separate square root terms together, we get 3 plus 2 gives us 5, and square root of 7s can stay. So we would have 5 square roots of 7. Now, if we, I'm skipping down to 3. Let's go over to 2. We have the square root of 3 minus the square root of 48. Now, just by looking at them, we can't combine like terms. We can't subtract these radicals because this 3 is not the same as this 48. But we got to be careful because in the last video, we talked about simplifying square roots. So maybe we can simplify this square root of 48 so that it eventually becomes possibly a square root of 3. So if we think about those perfect squares, just like in that unfortunate millionaire video, two numbers that multiply to 48 from our number line can be a 16 and a 3. So notice how the square root of 3 is kind of showing up when we simplify it. Alright, so we know that the square root of 16 is 4. Square root of 3 cannot simplify. And now, notice how we have like radicals. This is a square root of 3, this is a square root of 3. So we can subtract the outside coefficients. Now this is a 1, so I want to take 1 minus 4, which would give me a final answer of negative 3 square roots of 3. So even though at the beginning they are not like radicals, 3 is different than 48, maybe we can simplify one of them so that they become like radicals. Okay, that one was kind of tricky. If we check out number 3, this is a like radical to that, okay, exactly the same square root value, but this value of square root of 3 is different, so I can only combine like radicals. So I can take 4 minus 1, which would give me 3 square roots of 2, And since this square root of 3 is not a like radical, I cannot combine it. It stays exactly the same. So we were only really able to combine or simplify part of this problem. We have 2 values left compared to the single values we had in the other ones. So sometimes you can simplify everything, sometimes you can only simplify part of it. All right, it just depends on which radicals and numbers you're dealing with. All right, so number 4, notice how 90 is not the same as 40. So as they stand right now, we cannot subtract them. But maybe if we try to simplify them, we will get some like radicals. So from our number line, we can break apart 90 into the square root of 9 times the square root of 10. And we can break apart 40 into the square root of 4 and the square root of 10. So look at that, we're starting to get some like radicals. Square root of 10, square root of 10, we might be able to simplify or combine these like terms. Square root of 9 is 3, and then the square root of 4 is 2. So I have like radicals. Square root of 10, same as the square root of 10. So I can, in this case, subtract the outside coefficients. 3 minus 2 gives me 1. And just like up here, I can keep the insides. I can keep the square root of 10. All right, so not so bad. Just like combining like terms like you're used to doing, just make sure that your radicals have the exact same value. They have the exact same number. You can add or subtract the outside numbers just like you're used to doing. All right, so I don't think that's that bad. Let's talk about multiplying. This is where it can get a little tricky, especially in this case. If you look at number 6, we might have to do some distribution. But kind of similar to adding and subtracting, we have this whole outside, inside idea stuff. Now with multiplication, we can multiply the outsides because this 2 we can consider a like term with a negative 4 because they are both coefficients. They're both coefficients, they're like terms, we can somehow multiply them together. Now with this 2 and 6, both of those are considered radical terms because they're underneath a square root symbol. So I can multiply radical terms since they're exactly the same. They are like terms. So I can multiply the outsides, multiply the insides. Okay, just keeping everything balanced. So let's actually do that. 2 times negative 4 gives me negative 8. And then 2 times 6 can give me 12. All right, so I multiplied outsides, multiplied insides, and there's what I get so far, but we're not done. We could probably break apart this 12. Okay, we can probably simplify the square root of 12. We can break apart 12 into 4 and 3. Okay, 4 is on our number line. So we're left with negative 8 times the square root of 4, which is 2. And the square root of 3 has to stay. So our actual final answer is negative 16 square root of 3. Now I know some of us might be tempted to just leave that as our final answer, but we can't do that because the square root of 12 can actually be simplified. All right, so always check, make sure you can simplify those square roots. All right, so let's talk about some distribution. We have this radical term on the outside. We want to distribute it into the parentheses, and we're going to keep this idea of multiply outside, multiply inside. 4 times 3 can give me 12. 7 times 2 can give me 14. All right, so there's my first little swoosh. If we distribute the next one, this 4 is a coefficient, and this negative 2 is a coefficient, so I get negative 8. And then when I think about distributing in the square root of 7, there really isn't another radical number like there was here to multiply with it, so it just stays the same. We just keep that square root of 7. All right, now let's see. Can we break apart 14? Are there any square roots that can go into 14? No, not quite. And if we check 7, okay, that doesn't check out either. So since we can't simplify these, okay, we can't really do this process. And we also can't really combine like terms because this radical number is different than that one. So we can't just take 12 minus 8 because this radical term is not a like term with this radical 7. So there really isn't much more we can do with that one. We just had to distribute. Alrighty, let's go on to division. Okay, now I like this little picture up here. I think it's a really cool visual representation of what we're going to do. We're going to take a fraction inside of a square root, and kind of like the product property we talked about in the last video, we can break apart the two numbers and take the individual square roots. Kind of the same idea here. If we take a look at number 7, okay, we have one fraction inside of a square root. We can break apart that fraction into the individual square roots. Alright, that's not too bad. And what's nice about doing that is notice how the square root of 16, okay, is a whole number, we get 4. And the square root of 49 is a whole number, we get 7. Not so bad. Alright, let's try number 8. If we break apart the fraction, we can have the square root of 121 over the square root of 25. The square root of 121 is 11, and the square root of 25 is 5. Alright, so that one's not so bad either. So this whole idea of breaking things apart, showing up when we talk about division, and the last one we talked about, the product property last video, we can do that when we multiply as well. Alright, let's talk about rationalizing the denominator. Every time I say that, I kind of think about like some wrestling guy getting into the ring. We are rationalizing the denominator, and then everyone goes nuts. But I just think it's a funny phrase everyone hears. Alright, so this is where it gets a little bit tricky. We are going to multiply by a very special form of 1. When you take a look at this 3 divided by square root of 11, mathematically speaking, we don't like to have a square root in the denominator of a fraction. So what we're going to do is kind of be a little tricky, a little sly, and we're going to somehow move this square root of 11 to the numerator, or the top. Okay, that's why it's called rationalizing the denominator. We're kind of changing the way the denominator looks. So in order to do that, we're going to multiply by the square root in the denominator. So when I look at number 9, okay, the square root in the denominator is 11. So I'm going to multiply the denominator by the square root of 11. But you know, if we multiply the denominator by something, we need to multiply the numerator as well. And if you look at it, the square root of 11 divided by the square root of 11 is just 1. Anything divided by itself is just 1. And since we're multiplying by 1, we're not changing the value of this problem. We're just going to change the way it looks. So it's still going to have the same value. It's still going to have the same number equivalency, but it's just going to look a little different because we don't want the square root of 11 in the bottom. So let's talk about multiplying fractions, and we're also multiplying square roots. When we multiply fractions, we go straight across. And since I'm taking 3 times the square root of 11, this 3 is a coefficient, so it has to stay out front. And the square root of 11 is a radical number, so it has to stay inside the square root. Now, if we look at the denominators, 11 is a radical number, and this 11 is a radical number, so I can multiply those together. 11 times 11 gives me 121. Now, what's special about doing this, why we actually multiply by this square root in the denominator, is if you look at this, the square root of our denominator, the square root of 121, simplifies to a whole number. The square root of 121 is 11. But we can't really simplify anything up top, so it stays the 3 square root of 11. Now, I know some of you might be looking at this and saying, Miss Bites, okay, why can't we just cancel out those 11s? I mean, there's an 11 up top and there's an 11 on the bottom. But we can't do that because notice how this 11 is a coefficient. It's a regular whole number. This 11 is a radical number. Okay, it's underneath that square root symbol. So if this is a coefficient and this is a radical number, they are not like terms, so we can't just simplify them. Okay, like non-like terms cannot be combined or simplified, so they have to stay the way this is. This 11 is not the same type of number as this 11. All right, let's check out number 10. We don't want the square root of 4 in the bottom, so we're going to multiply by the square root of 4 on the denominator and in the numerator. If we multiply straight across our fractions, we get 1 times the square root of 4, which is the square root of 4. And the bottom, radical number times radical number gives me the square root of 16. Square root of 4 happens to simplify to 2. Square root of 16 can simplify to 4. And if we reduce our fraction, we get 1/2. Alright, so that one's not that bad, but I want to take a look at this one a little bit further. Some of you may have looked at this at the very beginning and said, well, isn't the square root of 4 just 2? So isn't this really 1 over 2? Isn't it just 1/2? Well, yeah, it is. And notice how we get the same answer. So I'm showing you this process, how we can multiply by the radical in the bottom and the top, and we still get this same answer in the end. So if you can simplify at the very beginning, go ahead and do that. It might make your life just a little bit easier. All right, let's check out number 11. We can break apart this square root into the square root of 8 and the square root of 5, but we don't want a square root in the denominator, so we're going to multiply by the square root of 5 over the square root of 5, and we're going to multiply our radicals. Now 8 is a radical number, 5 is a radical number, so I can multiply those. I get the square root of 40. 5 is a radical number, 5 is a radical number, so I can multiply those. I get 25. All right, now we have some radicals up top and the bottom, so we can probably try to simplify those. If we think about the square root of 40 and our number line, how we can simplify it, a perfect square that can go into 40, we have 4, and the other factor would be 10. The square root of 25 is 5, and if we simplify that, the square root of 4 is 2, square root of 10 has to stay, and we keep our denominator of 5. All right, so notice how with all these we are no longer having a radical in the denominator of our fraction. Okay, we're just somehow being strategic, we're being tricky, and moving the radical to the top in this fashion. All right, last one, let's check out number 12. We can break apart the fraction into the square root of 12 over the square root of 6, but we don't want square root of 6 in the bottom. So we'll multiply square root of 6 and square root of 6. All right, so let's multiply straight across. 12 is a radical number, 6 is a radical number, so I get 72. 6 is a radical number, 6 is a radical number, so I get 36. All right, run out of room, but we'll try to fit it in. If we try to simplify the square root of 72, we can break that apart into 36 and 2. And then the square root of 36 is 6. All right, so 36 can simplify, or square root of 36 can simplify to 6, square root of 2, and we still have over 6. Now notice this one, 6 is a coefficient on top, 6 is a coefficient on the bottom. Since they are like terms, we can try to simplify them. They will actually cancel each other out. So all we're left with is the square root of 2. Now, again, if you look at the very beginning problem, okay, if you can simplify it from the beginning, it might make your life a little bit easier. If we take 12 divided by 6, we get the square root of 2, which is the exact same answer we just got here. So this rationalizing the denominator process will always work, but always just try to check the problem at the very beginning, see if you can simplify it just a little bit further. That way you don't have to go through this work. But remember, rationalizing the denominator, kind of hard to say. It is a process that will always give you the correct result. All right, let's try some of these practice ones. All right, we're going to, in this case, we're going to add and subtract some rational, or not rational, we just did that, some radical numbers. And in order to do that, we know they all have to be the same number. We want a like term. Now, 7 is different from 28, which is different than 36, so I can't really combine anything the way it is right now. Let's try to simplify some of these radicals to see if we can get them to be like terms. Now, the square root of 7 can't simplify. All right, so we'll keep this the square root of 7 and the 3 out front. We can break apart 28 into the square root of 4 and the square root of 7. And we can break apart 36 into the square root of 9 and the square root of 7. So notice how it's starting to come together. See these square roots of 7s? Those are starting to become like terms. We might be able to combine some like terms in a little bit. So we have the 3 square root of 7. The square root of 4 is 2. And if I'm going to multiply that by this negative 2 in front of it, I get negative 4 square roots of 7. Plus the square root of 9, which is 3, and I still have the square root of 7. So now notice how all of these are like terms, they are like radicals. I can add the numbers out front. So we have 3 minus 4, which is negative 1, and if I add 3, I get 2 square roots of 7. Alright, so there's number 13. Alright, let's check out number 14, and I want to make sure we have enough room, so we'll kind of squish that down. Alright, number 14, we have this multiplication example, and we've always been talking about what this little power of 2 tells us. That little power of 2 tells us we have two groups of these quantities. So if I actually wrote them out twice, 3 square root of 3 minus 2 square roots of 2, and I have another group of that, 3 square root of 3 minus 2 square root of 2. Alright, so I want to multiply these together. Now we might have to go through this distribution process. So I'm going to take my first swoosh. Coefficient times coefficient gives me 9. Radical 3 times radical 3 can give me radical 9. Now I can do my second swoosh. Coefficient, coefficient gives me negative 6. Radical 3, radical 2 gives me radical 6. Alright, let's do our next distribution, our next little swoosh. Coefficient times coefficient gives me negative 6. Radical number and a radical number give me square root of 6. My next swoosh. Coefficient and coefficient give me a positive 4. And then radical 2 give me radical 4. Alright, so let's try to do some simplification. The square root of 9 can simplify to 3. So this is 9 times 3. And then we have negative 6 times. The square root of 6 does not simplify. So we can leave the second one the same as well. The square root of 4 is 2, so I can write my multiplication of 2. Alright, so 9 times 3 gives us 27. If we take a look at these square roots, they are like numbers. Square root of 6 and square root of 6 are like terms. So I can add the coefficients out front. Negative 6 and negative 6 give me negative 12, and I keep the radical 6. Now on the last part, 4 times 2, I get a positive 8. And last but not least, we can combine some other like terms. These are coefficients, those are numbers. So 27 plus 8 gives me 35, and then I have my minus 12 square root of 6. Alright, so there's our final answer for number 14. I want you to pause and try 15 and 16, very similar to the ones we just did. Try and see how you do. We'll be back in a second. Alright, let's check out and see how you did. 2 square roots of 5 can't simplify, but the square root of 12 can. We can break it apart into a 4 and a 3. We can also break apart 27 into a 9 and a 3. Square root of 4 is 2. Square root of 9 is 3. So if I take a look at my like terms, my like radicals, square root of 3, square root of 3, I can only add those coefficients out front. So 2 minus 3 gives me a negative 1. Square root of 3, and this 5 was not a like term, so the 2 square roots of 5 has to stay. Alright, let's check out the second one. We had to do some multiplication, some distribution. My little swooshes, I get 16 square roots of 25. My second one, I get negative 12 square roots of 10. My insides, I get negative 12 square roots of 10, and then positive 9 square roots of 4. Square root of 25 can simplify to 5. Square root of 4 can simplify to 2. And I combined my like radicals right in the middle. Square root of 10 is the same as square root of 10. So I can add the coefficients out front. I get negative 24. 16 times 5 gives me 80. 9 times 2 gives me 18. So when I combine those like terms, those numbers, those coefficients, I get 98 minus 24 square roots of 10. Alright, I hope you did awesome. Be prepared for tomorrow. We're going to do some more practice problems. We're going to add, subtract, multiply, and divide some square roots. I'm going to leave you with this awesome guy also showing you how important it is to know your square roots, and or not square roots, some perfect squares, and he's having a really good time with it.
Yeah, y'all know what it is. Mathematics. let's go.
I know you are looking around everywhere, looking for some perfect squares. I'm knowledgeable in many things. I know many things, almost everything. Give me a number quickly, times by itself, and you'll see that you will get a perfect square. A perfect square, a perfect square. So you wanna play with numbers? You see them coming at you with great force. A perfect square is the answer to a number multiplied by itself. Are you ready for a perfect square, perfect square? 'Cause once you start,
you'll be right on track.
These numbers can go on infinitely. Any number times itself and you will see. Doesn't matter how big the number is. The number is. Give me a number quickly, times by itself, and you'll see that you will get a perfect square. A perfect square. A perfect square. So you wanna play with numbers? You see them coming at you with great force. A perfect square is the answer to a number multiplied by itself. Are you ready for a perfect square, perfect square? 'Cause once you start,
you'll be right on track.
1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, 225, 256, 289, 324, 361, 400, 441, 484, 529, 576.
So you wanna play with numbers? You see them coming at you with great force. A perfect square is the answer to a number multiplied by itself. Are you ready for a perfect square, perfect square? 'Cause once you start,
you'll be right on track.